Hello everyone. So am I audible? Okay. Today we'll be taking a look at LeetCode Weekly Contest 481. Okay, so the first question was to find the mirror distance of an integer. So we are given an integer n, and the mirror distance is defined as the absolute value, basically the difference between n and its reverse, where reverse of n is the integer found by reversing the digits of n, return an integer, okay, and we just return the answer. Okay, so let's take a look at an example. So let's say our number is 480. In this case, so basically we need to take this number, reverse it, form this, its reverse would be 084, and we do not care about leading zeros, so we can just ignore that. So now how would we go about reversing a number? So to get each digit of a number, we can just perform modulo 10. So when we take 480 modulo 10, we will get 0. So we got our first place. Then we can divide 480 by 10, which will then give us, 480. We can divide 480 by 10, which will then give us 48. And now we can again repeat this process to get the next character. So again, if we take 48 mod 10, we will get 8. So why does this work? Because taking mod 10 gives us the remainder when the number is divided by 10, and the units place will never get divided. So the modulo gives us that character. So we can just keep on repeating this in order and generating our next number. So basically we can take our reverse number, let's call it rev, and initially we can set rev to 0. So as we get each character, we want to kind of send it into this thing. So to create an extra space, we can do rev into 10, which will then, let's say rev was 5, it will now make rev 50. And then the new character that we get, we can send it, we can just do rev plus the new thing, and we'll get 58. So let's run this for 480 and see how it goes. So initially my number is 480 and reverse equals 0. So then I take mod 10, 480 mod 10, and this gives me 0. Then I just do reverse into 10 to add an extra slot, but because this is 0 anyways, this operation has no effect. And then I just do reverse plus 0, the remainder over here, plus 0. And for right now this makes no change. Reverse is still equal to 0 after this operation, because when we reverse this number, these trailing zeros have no effect on your final answer, have no effect on the reverse number. Next, we divide 480 by 10, and that gives us 48. Now we again repeat the same process as before. So 48 mod 10 gives us 8, and then we do rev into 10, which again, because rev is still 0, has no effect. And so we are still left with 0. But now we add this remainder over here. So now it becomes 0 plus 8. And our currently reverse number is 8. Then now again I repeat the whole process again. I'll divide 48 by 10, and I'll get 4. And this is integer division. That's why it is not becoming 48.0 or 4.8. So when I do this, this means integer division. So I get 4 now. And then again I take 4 mod 10. Then I'll take this number, reverse. I'll multiply it by 10. And then I get 80. And then I do 80 plus 4, which gives me 84, which is my reverse number. So let's see how to code this out. Copy the template from here. And let's paste that in. Okay. So now we want to take a look at how to reverse our number. So let's, and if you notice, this reversing process does erase this number for us. So we should take a copy of it and then begin to perform this operation so that we still have an idea what the initial value was. So let's take rev equals 0 and let's create a copy. Let's create the m is going to be our copy of n. So now while n is greater than 0, so we want the current character, which will be n mod 10, and then we just divide n by 10, n slash equals 10. So now we need to add it to our reverse number. So we just take reverse multiplied by 10 and reverse plus equals a digit over here. And now we just need to finally print return the absolute value, the difference between m, which was initially n, minus the reverse number, reverse. Now let's see how this works. And in between we can also output to see the numbers, the initial m and the reverse number. Let's run this on the samples. Okay, there's an error over here. So what has happened here? Oh, this is supposed to be reverse into 10, not into 0. Okay, so as you can see, the initial number we got was 25, and then we flipped it to form 52. In case 2, the initial number was 10, and we flipped it to form 1. And in case 3, the initial number was 7. So now let's submit this. And it passes. A faster way to go about with this would be using the C++ using the C++ STL functions. There's a very convenient function to convert this to a string. So we can just call toString on n. Then we can call reverse on s.begin, s.end, which will reverse the string. And then we can convert our string to an integer again using stoi, string to integer, s. stoi stands for string to integer. And now let's see how this one fares. Yes, and it seems to pass on the samples. So as you can see, this is a much easier way to code out the first question if you can use the STL. Okay, now moving on to question 2. Minimum deletion cost to make all characters equal. So we are given a string s of length n and an integer array cost of the same length, where cost I is the cost to delete the ith character. And we may delete any number of characters from s, possibly none, such that the resulting string is non-empty and consists of equal characters. Return an integer denoting the minimum total deletion cost required. Okay, so because our input consists of only characters which are lowercase English letters, we'll have only 26 different kinds of elements within a string. So what if we tried to answer the question for what if we want to be only left with characters A? So from a string, let's say a string was A, B, C, D, A. What if I wanted to be left with only A's? Then I want to calculate the cost for that. Then I want to calculate the cost for being left with only B's, only C's, only D's, and so on. Okay, so to calculate this, so if I want to be left with only A's, I will have to remove all other types of characters. So if I want to be left with only A's, I will have to remove B, C, and D. If I want to be left with only B, I will have to remove A, C, D, and then A also. Similarly, if I want to be left with only C, I have to remove AB and DA. And for D, I'll have to remove ABC and then A. So can we efficiently calculate the cost to remove everything else except the given character? So we can calculate this by first storing the total cost. Total cost will be the cost to remove all the characters. That means cost to remove all the A's, all the B's, all the C's, and all the D's. Now, so that will basically be the sum of this input vector, the sum of all the integers in the input vector. Now, if I want to be left with only A's, I'm over here, I will be over counting, because if I want to be left with only A's, my total will even include the cost of removing all the A's. So I just need to take total minus the cost of removing A's. Cost of removing only the A's, because that much is getting counted extra, because I do not want to remove all the A's. I want to be left with all the A's, and I want to remove all the other characters. So how do I calculate the cost of removing just the A's? I can do that by maintaining a vector of size 26. So for every A that occurs, I will increment its cost. If A occurs at position I and has a cost of Ci, at position 1 in my vector, I'll add Ci over here. If there's another A that occurs at position J with a cost of Cj, I will add Cj over here. And then, so this will be my 0th index. I can have index 1, index 2, all the way till index 25, because we got 26 different kinds of characters. So for each character that occurs, we'll just keep track of the total cost to remove only that specific character. And then we can find the cost to leave only that character by taking the total cost and subtracting the cost of removing that specific character. So to recap, the total cost will cover the cost of removing A, B, C, D, etc. Now, if I want to be left with only A's, the total cost is overcounting this cost of A. I do want the cost of B, C, D, T, and everything. So I can take the total cost and subtract the cost of A from it. Okay, so let's see how to code this out. Oh yeah, we'll get to the third question next. There was a pretty straightforward solution to that one too. I'll show it in a bit. Alright, okay, so let's see how to code out our second question here. Okay, no, I don't even need my template here. Let's get the template from here. Okay. Okay, so let's, so instead of having to type out long each time, let's using ll equals long. Okay, now for each character, I want to store the total cost of removing just that specific character. Let's make a vector ll, because the sum of integers can overflow the normal integer bound. So we use an ll over here, and let's call it per character cost, and there are 26 possible characters, and initially all of the values should be 0. Now for each character in my string, actually I need the index of this, so for so let's get n, which is the size of my string, and now let's iterate through the string. Plus plus, so basically we'll do per character cost. And okay, how do I get the index? So I want a to map to 0, b to map to 1, and so on, and then z should map to 25. How do I change my character to this integer 0? I can just do this by simply subtracting a from my character, because it will then compare it with the ASCII values, and the ASCII values of all of these numbers are contiguous. So the ASCII value of b will be the ASCII value of a plus 1. So I can just take the ith character and subtract a from it to get the required index. And now I take my per character cost and I increment cost I. Okay, so now my per character cost will give me the cost of each character. Now I also want to calculate the total cost, and the total cost will be along LL. So total, and let's now I could go and like start total with 0, and then go for each. I could go for each index I less than n I plus plus, and then I do total plus equals cost I. But a much faster way of doing this using this C++ built-in functions will be accumulate cost.begin cost.end, and you want to add it to 0LL. If you use just a plain 0 here, that will take your starting value as an integer, and then if you keep on adding multiple integers to 0, you will eventually overflow the bound of your integer. Accumulate cost.begin. So, okay, so now we have the a total. Now we want to calculate the cost, the minimum cost. So now we'll check what is the cost if I remove A, what is the cost if I remove B, and so on. And we choose the minimum from that. So to choose the minimum, let's first initialize our answer to a very large value. So we'll keep on getting better as we find a better answer. Now for every cost in per character cost, so in per character cost, if I'm going to choose the character which corresponds to X, if I want only that character to be left in my array, in my final string, the total cost is going to be total minus X. So we can update our answer to reflect the new value if it is smaller by choosing the minimum between the previous answer and total minus X. Okay, so let's see how this works on the samples. Running on the samples, and it passes all my samples. Now let's submit it. Okay, and it passes the main test cases. So now let's take a look at question 3. Okay, minimum swaps to avoid forbidden values. So we are given two integer arrays nums and forbidden, each of length n. We may perform the following operation any number of times. Choose two distinct indices and swap nums I with nums j. Return the minimum number of swaps required such that for every index the value of nums I is not equal to the forbidden value for that index. If no amounts of swaps can ensure that every index avoids the value, return -1. So if it's not possible to satisfy the given case, we return -1. Okay, so let's take a look at the idea behind this one. Okay, so let's take a look at the third one with the proof, for like with a rough proof for like why it works. Okay. Yes. Okay, so now let's say our given array nums consists of, let's say, a bunch of 2s, let's say 4, 3, and 6. And let's say the forbidden values for this are 2, 2, 1, 1, 3, and let's say 6. Okay, so now let's first identify which all positions are at forbidden places. This one here, this one here, this is fine, this is fine, this is fine. These two are at forbidden places. So now we want to calculate the minimum number of swaps required to fix all of them. So now we can swap a given forbidden number in two ways. One is we can swap it with a different number that is not allowed in a position that is not valid, or we could swap a number with a different number which is in a valid position, which is in a valid position already. So let's see, when we perform a swap of type 1, we will be fixing, using one swap, we will be fixing two positions which are invalid. But if we perform a swap of type 2 like this, with one swap, in case 1, let's see, case 1, we're using one swap and we were correcting two of them. But in case 2, we are using one swap, but we are only going to correct at most one bad position. So first of all, we wanted to try to finish off all our swaps using only the forbidden values. To try to make all of our swaps happen only among the values which are not allowed for us. Okay, so let's see if this is possible. So let's take a look at which all numbers are not allowed right now. So there's a 2 which is at a wrong position. There is yet another 2 at a wrong position. There's a 3 and a 6. So, and because these numbers are at their wrong position, I am sure that the corresponding forbidden value is going to be 2, 2, 3, and 6 for sure at these specific indices. So I know for a fact that if I swap a forbidden number with a value I with a different forbidden position with a value j, it is always safe, because the forbidden value at position j is not equal to I, because, okay, this is assuming I is not equal to j. If we choose two positions I and, okay, fine, if we, let's take two indices I comma j such that I is not equal to j and the value at I is not equal to the value at j. Basically these are two different numbers now, and they're also at invalid positions. Then I can be sure that vi, the corresponding forbidden value, is going to be I, is also going to be vi, and the corresponding forbidden value at index j is going to be vj. So it is completely safe to swap these two values, because because after we perform the swap, vj will not interfere with the forbidden value which has a value of vi, and the vi on top, so this is our nums array and this is our forbidden array, and this vi will not interfere with vj. So basically, all this is to say that among my forbidden values, I can swap a given number with any of the numbers which are not equal to it. So I can swap 2 with the 6 safely, I can swap 2 with the 3 safely, I can swap the 3 with the 6 safely, but I cannot swap a 2 with a 2 safely, because that swap does not do anything for me, because their corresponding forbidden values are 2 and 2 itself. So if I swap the 2's, it is still, the placement is still invalid. Okay, so now I need to know whether it's going to be possible to perform all of my swaps within just my forbidden values. For that, the only case where it's not going to be possible is if I have 2's, there are, let's say, there are 3 indices where 2 is at the same place as a forbidden 2, and there's one 3 and there's a 6, and these are also at forbidden places. Now over here I can pair this 2 up with the 3, I can pair this 2 up with a 6, but this 2 does not have anything to be paired up with. But if this 2 were not there, or if I had, let's say, another index 6 with the value of 6, then I could pair this 2 up with that, and then with just 3 swaps my whole array is now valid. So now how do I classify this case? It is not possible. So let's say that TF is the total frequency of positions which match their invalid case. So in this case, my answer will be 6. The total number of invalid cases right now is 6. I will not be able to perform valid pairs if any frequency of a number, let's say this number occurs f times, in positions that are invalid. We don't right now we don't care about the valid occurrences. So if f, okay, and now the remaining frequency will be TF minus f is the remaining frequency. Let's call this r. So if r is lesser than f, then I do not have enough valid pairs for f to get paired up. So in this case, it will not be. So if for any f, r is lesser than f, then it will not be possible for me to form valid pairs. But the moment r becomes equal to f, some valid pairing will exist for sure, because when it's equal, we can see that I can just pair them up like this. But the moment it becomes unequal, I am unable to pair one of my indices. So this one gets left out. So to recap, if f is greater than r, or we can say f is greater than tf minus f, or we can say that 2 times f is greater than the total frequency, then I will not be able to perform a valid pairing. So now let's see, if I'm able to perform a valid pairing, then my answer will just be the total frequency divided by 2, because in each move we are going to pair up 2 of them. But what if the total frequency is odd? So in that case, we'll be left with one index that does not get paired up. We will take one extra swap to pair that one up. So it will be seal of this. And how do we perform seal while doing integer division? We'll just do total frequency plus 1 divided by 2, where this is integer division. Now we have to take care of the case where the frequency is greater than R. Okay, so if the frequency is greater than R, that means we are in some case like this, where we've got a bunch of 2's at places which are not valid, and then let's say we've got a 3 and a 6. And let's say we've also got a 4 at a valid place. A 4 at a valid place, and let's say a 5 at a valid place. And let's mark this in green. So let's say the corresponding value for that 4 is 2 and the corresponding value for the 5 is 3. And because these are invalid, their corresponding values will just be 2, 2, 2, 2, 3 and 6. So now we need to handle the case where the frequency is greater than R. So over here we can see the frequency of 2 is F, which is 4. And the frequency of the other ones that are invalid, the other values which are in invalid positions is 2, and 4 is clearly greater than 2. So now we come to our second case, our second overall case. To handle this, now we just need to see whether there is a valid pair for each of my 2's at an invalid place. So definitely all the numbers which are at invalid places will help out over here, because I can pair a 2 up with each of them. But now for my remaining 2's, I will have to find some value which is at a valid place and then swap 2 with that value. So now how do I go about finding which values from the safe ones? From all the safe ones, how do I go about finding which values I can pick? So if there's another 2 over here, which let's say points to a 5, there's no point of swapping a 2 with an existing 2 which is already safe. Let me mark the safes in green. There's no point of swapping a 2 with a number that's with the 2 that is already safe, because that will make this current 2 safe, but then the 2 that goes back in its place is now going to be unsafe again. So we cannot choose these kind of places. We can also not choose places where it is currently safe but the corresponding forbidden value is 2, because for a 4 a forbidden value of 2 is safe, but if I swap a 2 with that, it will not be safe. So basically I have to skip these kind of values too, and then I need to count the number of values basically where the forbidden value is not 2, and I can swap 2 with that. So the things that I care about, the nums I that I want to swap with is not equal to 2, and even the forbidden value at that position is not equal to 2. Then I need to count the number of occurrences of this, and if the occurrences of this is at least as much as the occurrences of the 2's I was not able to pair up, then my answer will just be the frequency of the 2's, because for each of these 2's I will have to perform one swap to pair them up. But if the occurrences is lesser than the number of these 2's, then I have no valid pairing, and in that case I'll output -1. So let's see over here, so if you notice these cases where we're trying to pair 2 with things that are already previously invalid, which are not equal to 2, I can still find them using the check that the forbidden value is not 2. So just performing these 2 checks on all the other numbers will give me my count of valid places to swap with. So let's see, over here I've got 4 2's which are at invalid places, and now for each of these other indices let's count. 3, 3, nums I is not equal to 2, it's valid, I mean it passes the first test, and the forbidden value is not equal to 2, it passes the second test, so I've got one number over here. 6 and 6, again it passes both the tests, I've got one more answer. 4, 2 does not, 4, 2, the first case is fine, the number on top is not equal to 2, but the forbidden value is equal to 2, so there's no point swapping a 2 over here, so this will not count to a tally. And then we find 5, 3, which is valid again, it both of our cases pass a +1, and then 2 comma 5. This fails our first case. So this will be a +0. So finally, the total number of valid places I can swap with is 3, but the number of 2s I need to swap is 4. So this is a case where I'll have to output -1. But what if this 4 were mapped to another 3 instead? Then this number would become 1. I would get a 4 over here, and because I have enough position to swap with, my answer will be 4. Okay, let's take a look at how to code this up. Okay, so let's go to file C, copy the template. All right. So first, let me keep a track of my unsafe places. So by unsafe, I mean invalid. So let's get n equals nums dot size, and let's create a map of, let's say, a map to an integer of invalid places. So this will count the number of times, let's say 2 will be mapped to the frequency of the number of times 2 occurs at an invalid place. And let's also calculate TF, which is the total frequency of invalid places. So now let's iterate over our vector. So if nums I equals forbidden I, in that case, this current thing is invalid. So let's increase the counter. Invalid nums I plus. We increment one counter, and we'll also increment the counter of our total number of invalid places. And now we want to see whether, okay, so now we've created our mapping. After this, we want to see whether there's any index which causes this case to fail, where the frequency of that specific element, the invalid frequency of that specific element is greater than the total frequency minus its own frequency. So let's take a look at that case. And if there can only be one such case, because if there's such a case, its frequency is already greater than half of TF. So you cannot have two separate values which are greater than half of TF. Only one such value can be there. So either there is no such value, in which case this will be our answer, or there is such a value. So initially, let's assume that there is no value. But if there's a value, let's say the required value will be, so initially we set it to -1 to indicate that we've not found any such value yet. And let's call this frequency of the value that we found, if there's an invalid value that we found. So now for every x comma frequency in invalid. Okay, so our condition was, if the frequency of our current number is greater than the total frequency minus its own frequency, then it's an invalid number. So in this case, we will mark it. We find out which our invalid number is, and then we'll also mark the frequency. So let us mark it as ans, because either this is going to be our answer, because now if this check fails, if this condition holds true, that means we'll have to go to our case 2. And in case 2, our answers will either be -1 if we were not able to find enough values to pair it with, or if we found enough values to pair it with, it is going to be the number of values itself. So the frequency of this one which occurs more than half of TF will be my answer. So how about we just store that in an answer variable. ans equals frequency. So now if after I perform this check, if the required value is still 0, I mean still -1, in this case I can just go about pairing the invalid ones with a different invalid one. So in this case my answer will just be, I can just return tf plus 1 to perform the seal. That's why there's a +1 by 2. Okay, now let's count how many valid places did we find. So now I know that I cannot swap with prepositions which will be invalid for these two. That means I cannot swap my given number if nums I equals required or if the forbidden value equals required. So I need to count my occurrences of values I can swap with. So initially it's 0. Now let's go for each index. So I can perform the swap if nums I is not equal to required and forbidden I is not equal to required. In that case I can increase my occurrence by 1. So now if my occurrences was greater than answer, greater than or equal to answer, where answer is my frequency of the most frequent invalid one, that means I have enough values to pair it up with. In that case my answer will just be ans. Otherwise it's not possible, as we saw, and the answer will be -1. So let's run this on the samples. Okay, it's passing the samples. And the overall code passes. So I hope this explanation was clear. Now moving on to question 4. Okay. So we are given an integer n and an undirected tree with n nodes, numbered from 0 to n-1. And this is represented by a 2D array of edges, where the array has a size of 2 and it just represents the edges. And this indicates an undirected edge between nodes ui and vi. We are also given an integer array group of length n, where group I denotes the group label assigned to that node. Okay, so each node has a certain label. Each node can belong to a certain group. And it's given that the group I can go from 1 to 20. That means we have at most 20 types of groups. Okay. So now two nodes are considered part of the same group if their group value is equal. Okay, so now an interaction cost is defined. So between u and v, the interaction cost is the number of edges on the unique path connecting them in a tree. So in a tree, the shortest path from one node to another is unique, and that will also be counted as the distance of node u from node v. So basically the cost is equal to the distance between nodes u and v. Now we need to return an integer denoting the sum of interaction costs over all ordered pairs u and v, where u is not equal to v, such that they are in the same group. Okay. So for a given tree, I basically need to choose all nodes which belong to the same group. Let's say this node is a group 1, group 1, group 1, group 1. And for all pairs of these, I just need to find the distance. So between, let's say, these two pairs, the distance is 1. So let's say this node can be paired up with here, here, and here. So for that, the distance will be 1. Distance to here will be 3. And distance here will also be 3. Now, this node, we won't pair it back with the previous one because it says an unordered pair. So an unordered pair does not care about the order of the elements. So 1, 3 is the same as 3, 1. So is basically it's the same as 3 comma 1. So we won't repair them up, because this node and this node, they were already considered when this node was looking ahead. So basically we need to take all, so we can think of it as the case where we choose all nodes I comma j such that I is lesser than j or something like that. So basically to ensure that we never take both the nodes, both the cases twice, like 1 comma 3 and 3 comma 1. So now this node over here can get paired up over here and over here, which will add +2 and +2 to our answer for that specific group. And this node can get paired up with this node over here, which will add another +2. Alright. So because there are only 20 groups, we can try to answer whatever time complexity. Let's say our thing takes O of x, where x is some time complexity. If we try to find the answer for every group, it'll just be O of 20x, which is the same as saying O of x, roughly, because 20 is not that big of a constant factor. So let's try solving our question for each group one by one. So now our question has changed to, for a given group, for group I want to find the interaction cost between all the nodes of group I. So basically find answer for all nodes in group I. Okay, so now let's see how we can go about with this thing. So let's first solve it for a general tree. A general tree where I want to answer what is the cost between all pairs of nodes. Let's forget the groups now, because we can take this idea and then generalize it to calculate the value for each group one by one. Okay. So let's say we start off with a standard DFS through our tree. So our DFS traversal will go something like this. We'll go down from our root, we go back up to this one, come down to this leaf, we go back up, come here, visit this one, go down, and then we finally go back up to our root. So if I wanted to, what if I answer this question for each subtree? For each subtree, I want to know the interaction cost between all nodes of this current subtree. So for that, I will take the leaf and then I'll try to pair it up with each of my children. And then again, I'll go down one level and then I'll try to answer it for this subtree again. And then I'll try to pair this node up with all of its descendants. So if we just go about answering, what is the cost if I pair the current root of a subtree with all of its descendants? I will cover a certain type of case where all my paths go downwards like this. Only downwards paths going from a subtree, from the root of a subtree down to its leaves. So for each parent I'll answer, for each root I'll answer, what is the total cost of this plus this plus this plus this plus this, and so on. So at least when I answer this for each subtree, I will have covered, when I'm looking at this subtree only, I'll cover these two. When I'm looking at this whole subtree, I will cover this, and this. and so on as I go to each subtree. So now that is one thing, root with children. That is one way we can pair. But now we will be, when we solve this for each subtree, we will miss two different types of pairing where they are not within the same subtree. For example, I will not pair this node with this other node because these paths only go downwards, strictly downwards, but this kind of path goes upwards and then it goes down. So now for each root, I also want to know how many ways can I pair it up with some element that occurs previously. How can I pair this given node with this one which occurs previously, with this one which occurs previously, and with this one that occurs previously. So, and I'll try to node with previous node. And by previous node, I do not want to consider some ancestor of this. I will not pair a node backwards with any ancestor, because technically before I reach this node over here, I will have come from the root and then this node over here. These do occur previously, but they are ancestors. So I do not want to count them because these pairings will get counted in my root and case. So I want to pair a node with a previously occurring node which is at least the same height as itself, or deeper. So basically I want to pair with only previous so that I do not count it twice, because if I pair this one with the previous and then pair this one with one that occurs later, I will end up counting that same path twice. So we'll only count paths backwards. So now the only way this node can get the information of the previous path is if the parent first calculates it for this path and then passes it on. So that is my case 2. So now let's see how will I actually go about with passing the values and actually performing all the required computation. So if I've got two nodes over here, both of these are at a distance of 1. So let's say the total distance over here is 2. Total distance is 2, and the frequency and the number of nodes in my subtree is currently 2 over here. So whenever a parent at one level higher wants to calculate its connections with lower nodes, the amount it will have to travel. So let's say the current sum is 2 and the number of leaves is 2. So basically the cost for this root of this subtree to pair up with its children will be just 2. But when I want to move it up and I want to pair this upper node with these two nodes over here, I have to traverse one extra edge. So for each of these nodes in the path, one extra edge is getting traversed. So I will increase my sum by this frequency count. So basically over here these two nodes will contribute 2, but over here these two nodes will contribute 4, because the contribution of 2 plus each of these two nodes will have to traverse one extra edge to reach here. So it will become 2 plus, so over here plus 2 because of the frequency. Now the cost will be 4, and then this node also will be contributing upwards, where the contribution will become 1 from here. So the total contribution will become 4 plus 1, and now the number of nodes in this subtree is 3. So 4 plus 1 gives me 5, comma 3, where my frequency is 3. So now if I want to see, okay, now how will this root pair up with these nodes over here? So now up till here the cost is 5. So each of these 3 nodes will have to traverse one extra edge to reach here. So basically I'll do 5 plus the frequency 3, because all these nodes, there are 3 separate nodes, and each of those nodes will have to traverse one extra edge while going on top. So my new contribution from these 3 nodes to the answer over here will be 8, and the frequency is still 3. Now we'll take a look at, now even this node is pending, this node is at a distance of 1, so that will change the frequency, the total cost to 9 and the frequency to 4, and so on. So if there was another node on top over here, I would do 9 into 4 for the contribution of this whole subtree, and so on. So the 9 into 4 over here should also reflect this subtree over here, and to do that we'll see that this node over here can contribute 1 with the frequency of 1 over here. Then this whole subtree, first this 1 comma 1 will contribute over here, and because there was one node over here which will have to travel 1 position extra, my answer will be 1 plus 1, 2 with a frequency of 1 right now, and then this new value, this new root on top, which will then become, increase my sum to 3 and my frequency to 2. And then obviously these two values represent this whole subtree, so I will just add them up. So this will become 8 and this frequency will become 5. So if you notice, I can just, to make this a bit cleaner, I can change this value to represent this whole subtree itself. So I can say up till here the cost is 1 with a frequency of 2, because let's count this node, but up till now we will not add anything to our cost because this node is at a distance of 0 from itself. But when we take this pair and we try to send it on top, both these nodes, these two, which is represented by 2, will contribute 1 1 to the cost because of this edge over here. So finally, when this subtree tries to contribute on top, the cost will become 3 because 1 plus 2 and the frequency is still 2. Okay, so that is the way we'll handle a root to a children. But how will I handle my node to a previous node? Now for a node to a previous node, whatever value this previous one passed on, let's say, so this one would pass 2 comma 3 up till here, and then this, when it reaches on top, it will become 5 comma 3. So this root, before calling the DFS on the next subtree, it should pass in 5 comma 3 over here, so that this node can then process the 5 comma 3 and then calculate the total length for node with the previous node type of pairs. So when I pass a 5 comma 3 over here, the same thing will happen again. The current sum is 5 and the number of nodes is 3. So by the time this 5 comma 3 goes down, it has had to traverse one extra edge. So when it comes down over here, it will become 8 comma 3. And then if you see 8 comma 3, so that basically means this node can pair up with the 3 nodes in this subtree with a total cost of 8. And let's see whether that's actually true. This is one option with a cost of 3, another option with a cost of 3, and then my final option, this path with a cost of 2, and that does sum to 8. Okay, so basically my root, when it's calling the DFS for the next one, it needs to send the accumulated costs or the contribution of the previous subtrees to my next subtree, and each subtree needs to return its own contribution to the root so that the root can calculate its own answer and the root can send that answer to the next subtree. And that is it. So that is the way we will calculate for just a normal tree. Now we wanted to do this for each group. So we can do that by just simply, we will not increase the count or contribution whenever a node is not of the type equal to the group that I'm currently processing. So the same idea with the same contribution will be run for all my nodes of group in group I. So let's say this is in group I, this is in group I, but this is not in group I. So let's see what the new contribution will look like. And let's say this node is also in group I. So now this node has a contribution of 0 to itself, because within the subtree there are no paths, but there's a frequency of one node which is equal to I. Then this will contribute on top over here. This portion will have no contribution. It will contribute 0, 0. Now by the time that this contribution reaches on top, it is going to become 1 because you have to traverse over one edge. So now this node is of type I. So we will take our global answer, and to it we will add, because this is a node of type I, it will count the contribution from its subtree. So this contribution when it reaches over here becomes 1, 1. So this one will contribute to my final answer. I'll do +1 over here. And now this one, now we update it for this whole subtree, because the value for this node should represent my whole subtree. So the current sum is fine, but now the frequency of I has changed to 2. We just increment that. And now 1, 2 will get contributed on top, and by the time it reaches on top, the contribution will now become 2, 2. But because this node is not of type I will not add 2 to my final answer, because there is no valid path with this at my root. Because when I'm processing only for group I care about the root has to be of type I, the child has to be of type I, or the previous node has to be of type I, and the current node has to be of type I. So the root over here is not of type I. So I will not try to make pairings with my root. So the contribution of 3, 2, which reached over here, because 1 plus the 2 frequency over here, because these two nodes will have to traverse one extra edge. So it will become 1 plus 2, which is 3, 2 will reach from this whole subtree to this node on top. Now this node will transfer the contribution down over here to form these kind of pairs. So when this 3, 2 traverses over this node, both of these nodes, the frequency, both of these two nodes, which is represented by a frequency of 2, will have to traverse this one extra edge. So now my contribution will become 3 plus 2, which is now 5. And this node is a valid node. It is of type I. So it will try to make pairs with the previous nodes which were of type I. So now I will add +5 to my answer. And we want to see that does hold true, because this path costs 3 and this path costs 2, and 3 plus 2 is 5, and this correctly reflects my answer. This node will have no contribution, and so on. So now let's just see how to code this out. So to recap, before we move on to the implementation, each node will return the contribution from its subtree for group type I. So we'll be running our iteration for each group, because we have only 20 groups. So for group type I, it will return the contribution of this group. And then the root, when it's calling the DFS for each subsequent subtree, it will give the contribution of the previous subtree to my next subtree. And then let's say there was yet another subtree over here. This root will aggregate the contribution of these two subtrees and then pass it on to my next subtree, so that I can perform this node and the previously occurring node, like that. And the root with its children of the same type. So now let's see how to code this out. Oops, sorry. Let me get the template from here. Okay. Again, because I'll have to work with a bunch of longs, I will make it easier by just calling it LL, using LL equals long. Okay, so now I'm given my edges. So let me convert this to an adjacency list. So I make a vector of int. Let's call it adjacency list, and it'll have n because I have n nodes over here. So now for each in edges, adjacency v0 dot push back v1 and adjacency v1 dot push back v0. Now I've created my groups, my adjacency list. Now we want to be able to calculate the depth of each node, and for that no, we do not really need the depth, because at each point we will just be incrementing it by 1. Okay, so now let's just go about with our final computation. So LL ans, this will be a final answer, and we will return it at the end. So now let's compute for each group. How about I equals 1, I less than equal to 20, I plus plus, because we have at most 20 different groups. That is given in the constraints over here. Now, okay, so let's define my DFS. I'm going to define it as a lambda over here. So I want to take in the adjacency list by reference and the group by reference. So, or I could just say I'll take everything outside by reference. Now now DFS, this is just normal lambda syntax. Okay, let's close this and so now let's see what all do we need to be passed into each call. Each DFS call will represent calling the DFS function for some subtree. So I need to know what is the root for the subtree, what was the parent of the subtree, and then for my specific computation I need this pair over here, the contribution. So each root has to pass the contribution of the previous set to each subtree, and the contribution has two sets of integers in it. One is the previous contribution and the frequency. So let's mark those. Let's call it LL previous contribution, and let's an integer called previous frequency. All right, so now for my root, my root will have to keep on passing forwards the accumulated or the aggregated contribution of each of the subtrees that we've already processed. So we'll store those in these variables called current contribution, the contribution of my current subtree, which will initially start off as 0, and let's say current frequency. Basically the number of valid nodes in my current subtree. Initially everything will be 0. So now let's process all of my subtrees. So now it will only be a subtree if the edge goes to something other than the parent. So if x is equal to the parent, this does not represent a subtree. This edge goes above our tree, not underneath. So we'll just skip this case because we do not want to go up to a parent. Now we need to call DFS for this new subtree. I just pass DFS in again because for lambdas that's the only way you can reference your lambda within the lambda. This is the most easy way I found for writing it fast. Now my new node, current node, which will be the new root of this subtree, x, current will now become the parent for this node. And now let's see, I have to pass in the previous contribution and the previous frequency. So that will consist of two parts. One is a previous contribution which came from on top. So let's see. So when I'm calling it for this node over here, I need to care about the previous contribution that might have come from on top and from the previous children within this same subtree. So when this root is calling DFS for this subtree, I care about the previous contribution from the other nodes, the other subtrees which were processed previously. And let's say there was some other tree. Let's draw a fresh tree. Actually, it's getting kind of messy. Okay. So let's say this node over here will receive a contribution from this previous subtree. A contribution will come down which represents over here. And there's also a contribution which comes from here. So both these contributions need to be passed on whenever I call a fresh DFS to a new subtree. So the contribution coming from on top, this one over here, is represented by these two, the previous contribution and the previous frequency. And the contribution of the previous subtrees which were processed right now with this node as the root will be aggregated over here in my current contribution and my current frequency. So let's calculate the new frequency now. So now the fresh contribution to my node will be the previous contribution, previous contribution plus the frequency, the previous frequency plus the current contribution plus the current frequency. And now the overall now this whole contribution represents the contribution by two sets of nodes, a previous frequency and the current frequency. So now the new frequency becomes previous frequency plus the current frequency. So that's all the parameters I need to pass in. Now my now as I said, each subtree is going to return its own contribution. So I can return it as a pair of long comma int. So the contribution will represent two things. The LL represents the sum contribution and the int represents the frequency. So that is the LL and the int over here. I'll just write that over here. Sum comma frequency. So that will be returned to me over here. So let's call that new contribution and new frequency. So now I need to update my aggregates. So current contribution plus equals the new contribution plus the new frequency, because all of these nodes will have to traverse these many nodes are there, and all of them have to traverse one extra edge. So the cost will get increased by new frequency, and my overall frequency will also get increased. New frequency. Okay, so now I have updated my aggregate, and so now as I keep calling DFS for each subsequent subtree, the aggregate will be passed in along with the contribution that came from on top. Now after I'm done processing all my subtrees, I need to check whether my current node, if the group of my current node is equal to the current group type that we are taking a look at. So currently we are taking a look at groups of type I. So if my current node is of group type I, then I will update my answer with all the edges or all the paths which end at my node. So how many such paths are there? So ans plus equals the contribution from my subtrees and the contribution which came from on top. And from on top, the contribution that came was previous contribution. And now in my current frequency represents the number of nodes in my current subtree whose group is of type I. So I'll increment current frequency by 1 because even my current root will add to the contribution now. And then I just return this current contribution from my subtree and the frequency of my subtree. And that is it. So now I just need to call my DFS. Initially everything can be set to 0. The current node I want to process is the node 0. I set the parent as 0 so that this case will never hold true because X will never have an edge to itself, so this will never cause a problem. And next, the previous contribution. So currently this is my topmost node, so there is no contribution coming from on top, and the frequency on top is again 0, so there is no contribution at all coming from anywhere. So now let's see how this works on the samples. Okay, there's a spelling mistake here. Correct that. And I need to put a semicolon. Okay, and it's passing all the samples. Now let's submit this. And yes, so this idea passes. So let's take a quick recap of how it works. So for each group, for my overall tree, during iteration I only care about group I. So now for all nodes which end with group I want to count a certain number, 2 kinds of paths. I want to count paths which are between root to child and node with the previous node. So root to child can be calculated when all the subtrees return their contribution to my root, and then my root can calculate this root to child. And node and previous will happen when the previous processing is done, and now the root, before it calls the next DFS for this subtree, it will pass in the previous contribution into the DFS call of my next subtree, and then each node which is of group type I can use the passed in values, the previous all the previous contribution from either a previous subtree or some previous node which was there on top of it, and so on. And then it can calculate how many the total contribution from these kind of paths, which is from a node to a previous node. So for this case over here, the root to child will only be this path over here, and the node to previous will be this path from here and this path over here. And I'm only going to count node to previous so that I don't end up counting this path forwards and then backwards. I'm only doing to a previous one, so it only goes backwards. And root to child, again, only root to child, so that I only check it from the root to the child and not backwards again. So each path is counted only once, and we do that for each group. So to recap, this is the contribution coming to my node from a previous node on top, and this is the contribution which is coming from the previous subtrees. Then I just add all of it, pass it to the next subtree. The next subtree will return the contribution of that own subtree, and then we update the contribution. If my group matches type I, then I will update my overall answer. So if the group is of type I, then for example over here, I will look at the previous nodes, and then for the now, that means this current subtree has one extra node, the current root, which is of type I. So I'll increment the frequency, and then I return the contribution from the subtree of this node, and then we run it for each group, and then finally my answer will reflect the total sum of paths over all nodes of the same type. Okay, that is all the questions for this for weekly contest 481. Thank you for watching.